fatigue. Okay, so I'm going to talk about fatigue, giving to you just 45 minutes, so it's not too short to talk about complex materials. But we'll be talking about homogeneous and isotropic materials subjected to fatigue, just to give you the general idea. In the end, with adjusting a little bit the theory, clearly you can use this idea also to deal with other materials, in particular with composites. Now, right now, for instance, personally, I'm using fracture mechanics and fatigue to deal with 3D printed polymers. 3D printed materials are really very popular right now, and it's an area where we can really reuse fracture mechanics. Even if I'm not a big fan of 3D printed materials, but hey, here we are. So, what is fatigue? We have a plate loaded in cyclic tension, and at a certain point, even if we see no real evident plasticity, we have a crack initiating and then propagating. Okay? So let's try to avoid the very first big misunderstanding. When we talk about fracture mechanics and fatigue, we don't talk about this phase when you see no cracks and at a certain point the crack initiates. In order to be able to use fracture mechanics to model the cracking behavior of metals, or in general terms of engineering materials under fatigue loading, you must have what we call a long crack. Okay? What is a long crack from a physical point of view? Okay, look at the shape of the crack here. Clearly it's a zigzag crack. It's really away from being a straight line. As we were saying before, actually, we can start talking about a straight crack if we really observe our problem from a proper distance. And the proper distance is having the effect of the local microstructure disappearing. For instance, in steel, you can forget about grains, you can forget about grain boundaries, you can forget about the local dishomogeneities you have. And you are really dealing with a material which is homogeneous and isotropic. Okay? So you need, and to reach properly that condition, you need a crack which is quite long. Okay? It depends on the application, it depends on where you are, but it must be a quite long crack. If you have a very high strength steel, clearly we can talk about a crack which is equal to 0.5 millimeters, but if you are dealing with a cast iron, it could be also a couple of millimeters, 3, 4, 5 millimeters. Okay, so we need to have long cracks. So this is fatigue, but actually fatigue and propagation is a quite complex problem, because if we see the same problem from another angle, you'll see here at the midsection of the plate, you'll see a little white spot appearing initially, cycle by cycle. Here we have this white spot appearing, and after a little while, you see that that is the crack initiation point propagating toward the two surfaces. You can see here the part of the crack being already appearing. Now the crack is moving toward the surface, and now the crack is eventually on the surface. And in general, what we see or we model is this propagation, but as you can see, this final propagation, now you can clearly see the crack here. This final propagation is the result of a very complex and initiation process. But now you should also be able to give yourself an answer. Why does this crack initiate here and not on the surface? Okay, it's a notch, it's not a crack. But now you can do the local stress analysis, and what would you expect to have here at the center of this plate? A kind of triaxial state of stress, or at least more triaxial than the stress you have on the surface. So physically, what the material feels is locally this state of stress which is more triaxial than the one you have on the surface. So you end up having your crack initiation happening at the midsection here of the plate. Okay? So, hopefully I'm trying to deliver the big message. And please keep it in mind over the next 2 days. We model reality. We don't invent the maths hoping that the mass we like describes something, okay? And in general, to have a rough idea about what's going on, there are a very rough idea. We don't need a very complicated models, okay? So don't fall in love with the maths, because we are interested in the phenomena. We are not interested in the modeling, or we are clearly interested in the modeling, but our modeling must be somehow linked to the reality we are interested in. Okay, I'm sure that you all know Umberto Eco. And when he talks about models and reality, he says that we must be very careful, because we might end up going to the restaurant and eating the menu. Because the menu is the model describing the dinner. But we are interested in the dinner, and we are not interested in the menu. So we need to use the menu properly to choose our dinner, and not using our menu as the dinner itself. Okay? And this is a very clever way to say, be careful, we love models because they are very useful. The menu can help you out to choose what you want to eat, but you are interested in the food, not in the menu as such. Okay? And this is what we are trying to do from now onward. Okay? Using fraction mechanics to model the fatigue behavior. Okay? So, basic definitions in fatigue. Clearly, and when we deal with the most simple case, we have 45 minutes, so we are just talking about the constant amplitude case and not the variable amplitude case, which is a completely different story. I would need a week to explore that problem. But when we deal with the constant amplitude problems, clearly the stresses we use to analyze our problems, still the nominal stresses, can be characterized by a maximum value in the cycle and a minimum value in the cycle. Accordingly, if the max and min values are known, we can calculate the amplitude, max minus min divided by 2, the range, which is max minus min, and is equal to 2 times the amplitude, the mean value, and finally the load ratio, which is the minimum stress divided by the maximum stress. If you look at this definition, for instance, an R value equal to minus 1 means fully reversed. This means that the mean stress is invariably equal to 0, okay? So, and this is a quantity we use in classic fatigue, but we also use this load ratio to describe the mean stress effect in the presence of longer cracks. Okay? So, if we go back to Irwin's plate, clearly now we can rewrite the equations we know in a different way, and actually what we usually do is expressing the problem in terms of ranges. So what we do is expressing K1 as the range of the stress intensity factor, and accordingly the stress components we can calculate via delta K1 are ranges. Okay, this is what we usually do, but de facto this is what we already know. Okay, we simply give a time variable meaning to these quantities, but nothing really changes. Okay, again we can talk about plane stress, and again we can talk about plane strain. Exactly the same problem as the one we have under static loading. And delta K is called mod 1 stress intensity factor range. Again, these weird units, unfortunately. Okay, so clearly, when we use the engineering definition we know for the stress intensity factor, if we use the maximum nominal stress in the cycle, we can accordingly define K1 max. In a similar way, if we use the minimum value in the cycle, we can define K1 min. And the range of the threshold value of the stress intensity factor, the one we use to calculate the stresses from Irwin's equation, becomes equal to K1 max minus K1 min, which is clearly alpha times delta sigma g, which is the range of the nominal gross stress, times the square root of pi times a. So we do our calculations again in terms of ranges. And the load ratio is defined as K1 min divided by K1 max, and if you play with these two definitions, it's easy to see that it's nothing but the minimum value of the nominal stress divided by the maximum value of the nominal stress. So we go back to the usual definitions we like when it comes to conventional continuum mechanics of fatigue. Okay, now let's assume that we have our plate with a crack, and as we saw from the two short videos, we know that cycle by cycle, under the applied cyclic loading, our crack becomes longer and longer, so the crack propagates. Why is that? Oh, that's a very fascinating question. It depends on your material and depends on your application. And my suggestion is have a look at the microscopic processes happening at the crack tip to better understand what's going on with your material. But put it this way, we take it for granted. You know, in a way, yeah, I have a crack, I apply the cyclic loading and the crack propagates. But it's not so easy to answer the most basic question, why? Why does a crack propagate? And also the other side of the coin is that why do cracks sometimes arrest themselves? Why do they stop propagating? So it's another interesting and clever question you should always ask yourself when modeling this phenomenon. Okay, anyway, if our crack propagates under the applied cyclic loading, we can easily build up a graph where we plot the crack length against the number of cycles here. Please note that it's the number of cycles, not the number of cycles to failure. Okay? So we are not talking about failure yet. We are talking about a crack propagating. I apply 10 cycles and the crack increases its length by 2 millimeters. Okay? It could not be failure yet. And now we consider two cases. The first case, the initial length is the same. The threshold, the range of the nominal stress for case A is larger than the range of the nominal stress for case B. And this is the way the crack propagates. And the crack keeps going, and at a certain point the two cracks will be so long that our plate fails statically under the maximum applied force. Okay. So first of all, we see something very interesting. You know, the larger the force, the faster the propagation. And this is common for all the materials. The larger the force, the lower the length at which your component fails. Why is that? Any idea? Okay, if you want, fatigue doesn't exist. Fatigue is a propagation problem, but we don't have a real fatigue failure. Why is that? Because even if you have a cylinder and you initiate a crack, the crack propagates under your cyclic loading, a shaft, and at a certain point, the maximum force in the cycle is large enough to break your component statically under the maximum force. So, technically speaking, a fatigue failure doesn't exist as such. It exists a propagation under fatigue loading. Okay? And clearly, if the delta sigma A is larger than delta sigma B, this means that the maximum force characterizing this cycle is larger than the force characterizing this cycle. And if you think about the definition for K1, which is proportional to the nominal stress, and this means that the maximum K1 in this case is much larger than the maximum K1 in this case. This means that we need a shorter crack, or in this case, we need a longer crack to be able to reach the critical condition locally. Okay? It's all there, all in the maths. The most important thing here is that at any point of our curve, we can define the tangent line. And the slope of the tangent line is dA, which is the length of the crack, divided by dN. And this is what we call the crack growth rate. Okay? Flat means no propagation. Vertical means fast fracture. In between, fatigue. Okay? That's it. This is where we are. If this is clear, we can then plot our results in a crack growth rate versus stress intensity range graph. And if we did that for our material, we would get results like this one, where the curves we know have got this kind of common standard profile, an inclined straight line here, and a kind of vertical asymptotic line here. Here again, you should know all the definitions, because stress intensity range delta K is defined this way. This is the usual formula we use for fracture mechanics, and this is the crack growth rate, dA over dN, which is the slope of the crack growth curve. So this diagram means that as the stress intensity factor increases, since the trend is this way, the crack growth rate increases, which at least makes very sense from a physical point of view. Okay, let's try to understand better the meaning of this diagram. So this is what we call Paris diagram. It was developed by Paris. The story I've heard from him is that basically he died a couple of years ago actually, and the story I heard from him is that he was dealing with this problem. He was approaching the end of his PhD. He was running out of money, which is very normal. So he had this bunch of data, and he tried to plot this data in a certain way. And by plotting the data, actually it was the other way around, but with this idea in mind, things started coming together. So there were two elements, according to the story I heard: being in the field and investigating that problem on one side, and on the other side, being at the end of the scholarship and being about to run out of money, which is a story which is very, very common, especially in the Anglo-Saxon world. Okay, so this is the schematic way of plotting the diagram. We have three regions. Region 1, which is delimited more or less by this vertical asymptotic line. We have a central region, region 2, where we have an inclined line, and since this is a log representation, a straight line in a log diagram is a power law. So our power law can be expressed as dN over dA is equal to C, which is a constant, a material fatigue constant, times delta K1, which is the stress intensity factor range, to the power of M. M is the slope of this line, okay? And when it comes to metals, if you want to get a reference value for M, I would say 3. And we have a third region, which is more or less delimited by this vertical line, where we have basically the fast fracture of our component. So how can we use then this diagram in situations of practical interest? Actually, it's quite useful, not very useful, but quite useful. So we can say that, first of all, we don't have to forget that given a material, the shape and characteristics of this graph and the position of the different lines depend on environment, the characteristics of the material. And what I'm saying that microstructural features here is that, if you get a piece of steel and for instance you heat treat your material in order to change the grain size, so technically speaking the designation of your material is still the same, but the microstructural features are different, because for instance you get bigger grains, and the fact that you have bigger grains can affect the position of the different lines in your graph. So be careful, because sometimes what we do is picking up these graphs from the literature, just because we see a similar material to the one we are interested in. But actually it's always very tricky, because even having a grain size which is slightly different from the grain size characterizing your material can result in a quite slightly different Paris curve. Again, we have the problem of the thickness, still dealing with fracture mechanics, but if we are in region 1, we can forget about the thickness, and the importance of the thickness increases as we move from region 1 to region 3. Again, another important aspect is the load ratio. Be careful, because the mean stress effect in fatigue is always a big issue. But anyway, assuming that we know all these things, how can we use this graph in situations of practical interest? Easy peasy. So let's focus our attention on region 1. Okay, we have this kind of line, and it's represented here, where here it's an old graph taken from a nice paper written by Keith Miller, and he used to call it crack speed, because this is just an idea about the way cracks propagate. So what does this diagram say? This diagram says that in theory, if your delta k, the delta k you apply is lower than delta kth, which is the threshold value of the stress intensity factor range, if you look at the crack growth rate, here it's very low. Be careful, this is a log-log diagram, so here it cannot be 0. This means that the crack propagation is different from 0, but so small that from an engineering point of view it can be neglected. And we have, in theory, no engineering propagation. But actually, if you look at the crack in this region, you would see that the crack growth or the crack speed follows a kind of zigzag path as the crack length increases. And why is that? Because still we are in a region where the crack is so small that the material morphology affects the crack propagation rate. So here you see, for instance, in metals, this zigzag path. It's because the crack has to run through the grain boundaries. And as we know, the grain boundaries are stronger than the grains. So you have a crack propagating very quickly when running through the grain and stopping at the grain boundary, so the crack growth rate decreases. And again, if we keep putting energy into the system, at a certain point our crack will be able to break through the grain boundary, running again very quickly through the grain and stopping again. But you see this zigzag path, and so we have a crack propagation. So again, it's consistent with the fact that dA over dN here in this diagram cannot be 0. But it's so affected by the crack, by the material morphology, that fraction mechanics as we know it is not a good theory to model it. Because don't forget that our fundamental assumption is that we have a linear elastic material, homogeneous and isotropic, at least to use this formula. Here the morphology plays a very important role, but in any case the crack growth rate is so small that when we are in this region we can say that the propagation is there, very small, but it cannot be measured using these tools. And this brings us back to another problem, which is inspections. You know? What engineers do when it comes to real components is every now and then inspecting real structures, and they see a crack, and the calculation they do is to check if they are still in this region. If they are still in this region, they say, okay, I know that the crack is there, we'll keep monitoring it. We know that the crack is propagating very, very slowly, but still with this diagram we cannot predict the crack growth rate. What they do is keeping monitoring the crack until delta K for that crack becomes equal to more or less delta KTH, because they know that from that moment onwards they would enter region 2. So if you see a crack in a component and the associated delta K1 value is in this region, you can say that for the time being, of course you want to keep monitoring the crack, but from an engineering point of view, that propagation is so slow that can be neglected. We know that sooner or later it's going to happen something, but still we are feeling good. Okay? So in terms of design, if we say that our delta K1 is lower than delta KTH, we are here, according to Paris schematization, we can say that our crack is not really propagating. Okay? We know that is not true, but this is the consistent answer. Okay, still we inspect our component, we know the shape factor for our crack, and one day we discover that our crack results in a delta K1 which is larger than delta KTH, so we are well within region 2. So, in that case, we want to know the crack growth rate, or how many cycles we need to make the crack propagate up to a certain length, for instance. Cycles can be days. I don't know, if I have a chemical process and I need 1,000 cycles a day, and my crack needs 10,000 cycles to propagate, I would say, ooh, I can work for another 10 days and that's it. So it depends on what are your units, but in the end it's the lifetime you want to measure, and it depends on your specific application. This part of the diagram, region 2, is very much affected by environment, microstructural feature, thickness and load ratio. In this equation, as we were saying, C and M are material fatigue properties. Okay? We are dealing with the metals, but for instance, you can find similar graphs also for composite materials. It's very difficult because in that case you really need to give a lot of details about the way you were running your experiments, the orientation of the fibers, and blah blah blah. But overall, they tend to summarize the story very often using this simple power law. So nothing nothing else to say. If we can calculate delta K1 and C and M are known, we can estimate the crack growth rate. This is an information we can play with in order to make, for instance, further assumptions. Finally, now the question is, how do we use this information? Because we have this formula, but as it is of little interest unless we play an interesting game. So if we define little n as the number of cycles to failure and nf the number of cycles to failure, which can be the number of cycles you need to reach a critical configuration. It couldn't be like just the complete failure of your component. You could say up to this point my component is safe. After that I don't want to risk, or it's too risky for me. So it's a failure in general terms. Okay? So when your component is no longer usable, it doesn't mean that your component must be completely broken. And if we have a crack, initial crack having length AI, and we assume that AF is the final crack length, that is, for instance, in this case, is the length of the crack resulting in static breakage under K1 max, what we can do is stating the obvious. It's the only model I know in my life, or I know in engineering, where you get something useful by stating the obvious. The obvious is simply saying that if I want to calculate the number of cycles to failure here, I consider all the cycles that take me from 0 to the number of cycles to failure. It's trivial and it's absolutely stupid, but if you start stating the obvious, you can say, okay, now I multiply this quantity by dA, which is the crack increment, and I divide this quantity by dA. So you can do it because it's 1, the ratio is 1. But this allows you to rearrange your quantities here by changing variables. So you can say, since if my number of cycles, when my number of cycles ranges from 0 to NF, clearly the length of the crack must change from AI to AF. Now I can rewrite my quantity this way, and my new independent variable is dA and no longer dN, so I change the variable. I can do it because the boundary conditions are consistent here. Here I'm tackling the problem in terms of number of cycles, and here I'm tackling the problem in terms of crack length. But AF corresponds to NF and AI corresponds to 0 in this schematization, so there is a perfect consistency between these two terms. But if we focus now our attention on this term, we can use Paris equations here to express dA over dN, which is C times delta K1 to the power of M. So now we have this final equation where delta K1 is the usual formula we use, is the engineering definition for delta K1. It's alpha times delta sigma g times the square root of pi times A. Okay, let's have a look at this formula, which is not easy to integrate, by hand. It's very easy to be integrated by using MATLAB or MATCAD nowadays, but when this formula came out many years ago, it's around the 60s, it wasn't so easy to manage. And now let's play with this formula a little bit. So let's make an initial assumption. Let's say that alpha is constant. We know that is not true because the shape factor given a component changes as the length of the crack varies. So it's a very, very restrictive hypothesis, but let's play with the mass for the time being, and let's form this simple hypothesis, and we can see how can we sort out this problem at the very end of the process. So if we assume that alpha is constant, and we know that C and M are material fatigue constants, these are the constants we find in the Paris equation. We know that delta sigma g is constant because it's the range of the nominal stress, and we are dealing with a constant amplitude problem. We say that we are not treating variable amplitude fatigue here. So C, M, delta g are constant. According to this assumption, also alpha is constant, so pi is by definition a constant. So we can get rid of all the constant quantities, knowing that alpha there is something very, very, cheeky to do, because we know that alpha changes a lot. But if we do so, we end up with this very simple term to integrate. So it can be integrated by hand, and this is the final formula we get, which is valid if alpha is constant. You might have certain cases where the component is so big that the variation of alpha is so small that you can assume that alpha is constant, but actually it's not, it's in general it's not the case. So one trick we can use to sort out the problem is simply assuming that if this is the way the shape factor changes as the crack length increases, we can subdivide our propagation range into a number of sub-intervals for which alpha can be assumed almost constant. So what we do is calculating the number, we use this formula, and we calculate the number of cycles we need to move from the beginning of an interval to the end of the next interval. After that, we change the shape factor, and we need, and we calculate the number of cycles we need to move from the beginning of the second interval to the end of the second interval, and so on. Clearly we are introducing an approximation, but we are considering a number of sub-cases for which alpha can be somehow assumed to be constant. If we know the number of cycles to move from the beginning to the end of any intervals, in the end we can calculate the number of cycles to failure by putting together the contributions coming from all the intervals we use to define, to schematize our problem. Job done. It's very useful. You can do your calculations by hand. But actually, nowadays, really, this is no longer an issue because we can easily integrate this equation numerically by taking into account the fact that alpha changes. Okay? But this is just a very good way, if you are not already familiar with this equation, to play a little bit and to get familiar and to understand how things change in terms of shape factor, crack length, the mutual interactions amongst the different variables. So it's an educational tool, and it's also to show you what the people used to do in the past. Nowadays, clearly, a conventional computer and a simple code are enough to solve this problem. And finally, we can move to the third region, where basically what we have is that this region clearly doesn't exist. Why is that? Because as the crack increases, clearly the crack growth rate increases and delta K increases. So if we start from here and we keep propagating the crack in the Paris region, we move along this line vertically. At a certain point, K1 max, the maximum stress intensity factor value in the cycle, becomes equal to Kc. So basically what you have is a fast fraction under the maximum applied loading. This is the reason why here you have this vertical line. So basically this is the static assessment. But if we want to put everything together in a consistent way in this diagram, what we need to do is a very simple calculation. We know that by definition delta K1 is K1 max minus K1 min. We know that the lower ratio is also K1 min divided by K1 max. This means that K1 min is equal to R times K1 max. According to this definition, then K delta K1 it can be also expressed as K1 max times 1 minus R. So we can say that K1 max become, or if we can say that when K1 max is equal to Kc, delta K1 is equal to Kc. This means that we can calculate the delta Kc, which is this value here, which is the range of the stress intensity factor, resulting in a maximum value for K1 equal to Kc. Static breakage is the end of the story, and we go back to the first part of this chapter about fracture mechanics, because here this is the static region. Here you have delta K1c. Okay? Here we are. Any questions, comments? I'd like to talk about fracture mechanics. Exhausted. Okay, any questions, comments? Sharing your experience with fracture mechanics, particular problems. Was everything clear enough? Hopefully taking you gently into what we are going to do over the next couple of days. This is it, enjoy your coffee then. I think that I talked to Francesco, and basically as you said at the beginning, you can go to the bar directly with the small tickets and you can enjoy your coffee. Okay, so I'll see you around, and if you have any questions later or whenever during the conference, just please ask. Thank you guys.